Hi everybody. My name is Sebastian. I'm working as a consultant and trainer. I'm a freelancer, mainly in a topic many people would call enterprise application integration. And yes, I'm today here to show you durable Azure Functions. Up front, would like to ask you some questions to check out the experience level. Who has ever heard of Azure Functions here? Please raise your hands. Okay, that's pretty good. Who has actively worked with Azure Functions? Okay, 3, 4 hands. Okay, that's good. Does anybody have heard about durable Azure Functions before this talk? Okay, that's even better. Did anybody tried the durable functions before this talk? No. Okay, that's good. So we have 50 minutes to go in deep, and I did a little plan for us, and I would like to start to bring everybody up front we do some Azure Function basics, but just roughly in 5 minutes, and afterwards I would go directly to durable Azure Functions, and then I have after a lot of theory, I have a real-world sample, which I created for you to show the capabilities of durable functions in a real-life sample. And finally, I hope we have some time for Q&A. So let's go ahead. Just a small recap for everybody and for the people who never heard of Azure Functions. Maybe it's a good introduction. What are Azure Functions? Azure Functions are the serverless a function as a service solution of Microsoft Azure, and basically it's just running. It's that simple as the picture. It's code. You execute some code on a platform, and you don't care where that happens, how that happens. That's serverless, yes. And you have an input and you have an output of a function. That's roughly what Azure Functions is. It's your code running serverless anywhere, and they have a lot of supported languages there. It's not just their own languages like C# or F#. We have Node, JavaScript, we have Python, PHP, Bash, PowerShell. In the runtime too of Azure Functions, we have Java as well. So there are people out there which tried that out with the Java runtime. You can even use Kotlin if you want. That's no problem. So you have your preferred language there. No need to learn anything else to run that on the platform. How does it work in detail? On a high-level abstraction, that's your code in the middle, and you have some bindings. And the bindings tell the runtime how the input gets in your function and the output gets out of your function. And then you have a trigger binding which tells the runtime how your function is triggered. That's all. So, and that's pretty declarative. And there are different ways to do that, but that's the main pattern to do that. Yeah? It's your code, and then you put out some binding in there and tell the runtime how to run the code, where to get the input, and where to put the output. And yeah, fairly that's it. And yes. And you can have multiple in and outs. That's not a problem. So, durable functions. What are durable functions? Durable functions is an extension of Azure Functions that let you write stateful functions in a serverless environment. That's the definition. So it's an extension on the normal Azure Function runtime there. And what does that? The extension manages the state, checkpoints, and restarts automatically the process for you. It enables you to have a stateful function. No? In serverless in general, even on other platforms like OpenWhisk or AWS with Lambda, function is always stateless. So you run a function and the function has a state when it's running, but it's no persistent state. If the function crashes in the middle or the runtime tears down in the middle of the execution of your function, and normally everything is lost. There's nothing left. It's just stateless. Yes, and durable functions is an extension that enables you, if you need to, get some state in your functions. That affects mainly not the small pure functions which you just execute and just calculating some values. That affects mainly the functions where you start correlating, where you start orchestrating some other functions or orchestrating some kind of flow. Because of course, it's function as a service, and most of it's pretty pure. But code is not just living in small, isolated, pure functions, and you mainly you need some drivers around that to drive some kind of business process, and therefore you can create some state here. You can define workflow in code. That's the important message. You don't need JSON designers or anything else. You just code, as you always code, I assume. You code your flow, and it's totally transparent at that point. You code your workflow, and your workflow automatically gets a state from the extension from the runtime below. Durable function extension is just a NuGet package for SIG. You just can download it, and you can even run it locally if you want. As all the other Azure functions, you can try to debug it locally. You just load it, and the extension plugs in the runtime and extends at the extensibility points and ensure that you have some durability. Yeah? That's optional. If you don't need it, you don't have to. You can use it in case in one function and in the other one function not. If you don't need it, it's totally optional, and it's pretty slim. Technically, the durable functions are based on the durable task framework. Microsoft started that some time ago, which is a extension for developers on the TPL, on their test parallel library. When you do some async await stuff, yeah, you can use that in the manner that this library or this framework persists the state for you. It's the same pattern, just on the programming language level. And the durable framework extension just picks the principle up and uses it and binds it to the function runtime for you in the best way you want to see that. Yeah? It's based on event sourcing pattern, means, not to go in depth there, they don't save a defined state in their storage of your workflow. If your workflow goes down, they don't have one state for your workflow. They have several events. They knew, okay, you executed that event, and then you executed that action, and you have a sum of many events, and that sum of events in an assay is the state of your orchestration. And that's the event sourcing pattern. Microsoft did not invent that. They just used that as a solution for that, and I think that's the pretty right solution to do that. Event sourcing below. How does that work in practice? The orchestration function, you can write automatically checkpoints at several points, the progress whenever you await a function. So it's some kind of natural when you're coding your orchestration functions. Everywhere where you are awaiting for somebody else which is doing something, because an orchestrator did not work. The orchestrator is just there for orchestration. So the orchestrator normally defines the flow in code and then calls functions which does the work. And at every point you call a function which does some work for you, there is a restore checkpoint for that. So he automatically set up the restore checkpoint. So in case your orchestrator clashes and he has to resume, yeah, he drives the whole process again, and at that point, when you call a function B from your orchestrator, he checks, hey, do we already have called that function B in a previous instance? And then he say, yes, we have, and we have a result for that call. Okay, just take the result, never call it. So and that's the principle, that's the way he recreates a state and uses that state to resume your process without driving the whole thing again. Because if your function crashes after, I don't know, 8 minutes calculating, then you're done. 8 minutes lost. But not in that way. Yeah? You just lost the work where he cuts off at that point. Local state is never lost. If the process recycles, the VM reboots, the runtime crashes, could all happen. Yeah? But it's not a problem for you. You don't have to pay for that. If you have paid 8 minutes of calculation and everything is lost, you just have to pay for it. On serverless too. Nobody will give you the money back. So if the runtime crashes, it's not your fault, but you have to pay for it. And in that case, you have the results. You just can resume at that point. To bring that in practice, I have some common patterns here to show you as an illustration and in code, because we have orchestration as code. And yeah, finally, I will show you some of that patterns in a real-life example. First up, I want to show you function chaining. That's the simplest thing. Afterwards, we go to fan in, fan out. Common pattern out there. We have some async HTTP APIs or async process start and monitoring and watching the process. We have monitoring. We'll have a look on human interaction. That's a very long-running processes most of the time. When we have human interaction, they don't get a mail, click on it. They have some time and they click tomorrow and the next day after. And then you have long-running processes. And human interaction is often an indicator for long-running processes. And I will show you how to handle that with durable functions. And I will show you how to do sub-orchestrating. That's simply the pattern, not to call some functions doing the work, but you can partition your process in reusable orchestrations. So you have sub-processes which you want to reuse. You can start them as their own, or you can have an orchestration above which use many of them. So you can start some pattern of, you build up some components, or you're aggregating your processes, depending on how you like to name it. Let's go ahead with function chaining. Pretty simple. We have a process which should cover, we want to call a function 1, then we want to call a function 2 with a result of 1, and finally we want to call a function 3 with a result of function 2. So we have a simple chaining and we have a dependency, so we cannot call them in parallel, so we have to wait for each result to call the next one. Just a simple process. And what happens if after the function f2 the runtime fails and the process crashes? So everything is lost. 5 minutes of calculation. Lost, done, splashed. How can we do that? In a pretty simple code snippet there, and yes, I've used C#. C# is, I think, some of the mandatory languages at the moment. In the function runtime 2, and they promise they will have all the languages, I think most of the languages on board, so you can do that with Java and other languages too. Not all the languages, but many of the languages in the future. Currently, you're restricted to C# and I don't know, maybe F#. Yes, that's pretty easy. That's the function. And how does it work? We have a declaration up there, the function name, which I call orchestration. I don't know if that's perfect. And the function has just the name run. And there's a parameter which introduces the context in there. And the context is injected by the runtime, so we don't have to care about it. We trigger that orchestration, and then we just write that argument in there, and the runtime knows, you want to have the context of your own instance, no problem, there it is. So the binding happens automatically, you don't have to care about that. Sorry. And then you just go on and just call a second function, or the function f1 from your orchestration, with no parameters, and you use that context.call activity async. And finally, you just await your call. It's just as if you're coding. You don't call it directly. You don't call f1 curlies, null curlies. You just use that mechanism, but you have a regular task in here. There's an await in there, and you have a result, and that's you await that call. And what happens in the background is the runtime decouples your call. It's not called directly. It just puts a message somewhere, and then the runtime comes back and says, I have to call that function. Okay, let's call it. And when it comes back, then your orchestration is reactivated, and then the result is in there, and it drives through and goes further. What's the benefit of that? The orchestration is not running when it's waiting. And as with all serverless constructs, you have to pay for the runtime. And in that case, you don't have to pay. You just pay the caller, which is working, but you don't pay the orchestration for waiting, which normally you would do if you wouldn't have that on a regular function base. And that's the most benefit. If you're waiting 2 minutes for a result, you can pay for the orchestration doing nothing, just waiting. Or using that mechanism and pay nothing for it. I think that's a great opportunity. And it's that easy. If you look at the code, you call the second function with the result of the first one, just put it in, and then you call the third one with the result of the second one, and then you just return the value. That's normal coding as you would do it normally, I think. And it's that easy to bring that in your code, and you have fully managed state in there. If that crashes on F2, no problem. Second pattern is fan out, fan in. Fan out, fan in is a great example pattern for durable orchestrations because that's a point where you can really lose some money if something crashes, and it's a good opportunity to show that. Okay, let's have a look in the code. So we just have an orchestrator, and at the beginning we just want to check we get our work batch. That's the most important part. We call a function which determines what work we have to do. That's a good option. And then we have an array of object work batch there, which now has to be processed, but can be processed in parallel. So, but we don't just want to spread that out. Yeah, we have a loop in here. We don't call all the workers, I call it the workers now, where we have a fan out here. We don't call them directly. We call them again on the over the runtime option, but we don't await them. Yeah, we just summarize the tasks there. We just remember the task in a list. So at the end, it just spreads out. We have a list of tasks we have to wait for, but these tasks are not running currently in my process. Maybe the runtime can decide where it wants to run that functions. So if that later scales, crossing, I don't know, somewhere below bare metal, anywhere, I don't care. I just call that function, and if I have, I don't know, tens of thousands of items there, the runtime can just decide where to execute my function, on which host, on which, it just can do it on their own. But they're fully stateful at that part. And afterwards, we just would, as normally, we would just await and say, okay, let's wait when everything is done. We just do the fan in again, at that point. And finally, we have all the results. We do some sum on that. We say, I don't know, we either have a order amount per customer, and then there is some, and then I call the function tree, and that sends an email and says, hey, we have performed great. We have so much turnover. Yeah, and it's that easy. It's completely stateful at that point. When we have a look, if the work batch is done, and we have the spread out and then the fan out, and if one of the F2 function fails, only one, we don't care. All the other ones will run, will finish, and when there is an exception, we will say on later, it just populates then. And it will just populate if you would expect an exception. It would just race through and crash your orchestration, and then the orchestration runtime, the runtime behind will pick up that again and to say, okay, we do a retry. And then it will start. We have the work batch again. Okay, work is already determined, no problem. It runs, it spreads out, but except the one which failed, no of the F2 function will be executed. So it just runs through, awaits the one, and then do a sum, and then call F3. So probably you're done then, hopefully. And you don't have to care at which point in the whole scenario it crashes. It just will recover for you. Next pattern is Async HTTP APIs. That's a pretty specific pattern name, which is probably the principal pattern. We'll see that later in the example too. You start a process, but you don't want to wait because it's pretty long running. Yeah, maybe it's running, I don't know, 5 minutes. You have an HTTP caller there which has a 2-minute HTTP timeout, and he will definitely not wait for you. Yeah, that the orchestration finishes. Or maybe you have some further interactions and the whole orchestration is running for days. You couldn't await that. So the pattern is you want to start a process and then up there. And then the process runs in the background. You don't know. Depends on your settings, depends on your orchestration and your function in the workload. It does the work and it persists its state. And then you regularly pull the state and say, hey, are you ready? Are you done? And the benefit in there, I will show you in a second in the code, is, that's pretty slim code, is that the runtime has an option in there to provide you some nice thing. It's again just a function. I call it the orchestrated HTTP start function, which then gets a binding for HTTP and automatically gets a public endpoint if I want to. And I just call that endpoint. We will see that later in the sample. And I have that durable orchestration client starter there, which is an option which I get injected to start an orchestration, or many orchestrations, as I want. And that's a universal starter, so I have a function name in there. It pulls out the function name and then starts my function, and then gets an instance from the engine that's start new async, and you just type in the name of the function you want to call, and then he starts that orchestration. It should be an orchestration function, of course, and then you get an instance ID, and that instance ID you can work with. The runtime has some options. You can call the runtime and say, hey, do you have a status for me? Maybe you want to signal some event to the orchestration from outside, say, hey, I have some news for you. We'll see that in the human intervention sample later. Or you can terminate it. You say, okay, we're done. Break it down, cancel it. Yeah? And to make it a bit more easy, they created that starter create check status response, which just created an HTTP response, just pretty simple JSON with 3 links in there. One link is for where to call for signal an event, where to call for status, where to call for termination. And it automatically generates a deep URL to the engine, which has API endpoints in the background, and then you can call that endpoints of the runtime, of the durable functions runtime, extension runtime, and ask for the status, of course, if you're permitted to. And then you can call the status, I don't know, every 10 seconds, 30 seconds, minutes, as you want, and then you get detailed information about how the status is. Or you can terminate if it's running too long for you. That's a second option too. And that's pretty easy and pretty handy. So you start a process, you have an instance ID, and then you can go to the runtime and say, give me the status. How is it working? Has it failed? What was the error? What was the outcome? We'll see that in that sample. Then we have the monitoring pattern. The monitoring pattern has roughly some same aspect at what I told you some seconds ago. Monitoring means I have an orchestration and I want to monitor a second orchestration or a second process or something which is running. This is just a pattern. That's not that much about techniques. It's just how you can use the options of timeout and create timer there to get some kind of monitoring. So in case I have an expiry, I say, okay, I will want to pull a process about 10 minutes. And I check the time, and I have a while loop. Yeah, that's a while loop with a state. And I have an expiry time, and then I have a job status here, where I pull I have just a function there, which I call for the status, and if the status is completed, I say, okay, we do that, and if not, we just wait. And then we add some seconds to our interval, and they create a timer, and we await that timer. And then the best thing in that part is, of course, it places a callback on that time, and then the orchestration goes down, and you don't have to pay for the waiting time. Yeah? You're not waiting for a call, you're just waiting for time. And that happens. And then you come back and check a status, yeah, and say, no, still go to sleep. It's kind of sleeping, yeah, but unpaid sleeping. Yeah? You don't have to call some activity to do that. You can just create a timer. A specific task that enables you to schedule some wait time you don't have to pay for in your orchestrator. Pretty roughly simple construct there to enable that in your orchestration. Then we have human interaction there. Human interaction, and I have the picture is just an example already there. There are many ways of human interaction we could imagine. My example is a request approval. So you have some kind of process which somebody sends in a request for, I don't know, want to have a new laptop or something like that. Somebody has to approve that request or deny it. And then you have a small process, and the runtime sends out, a request to the approver and say, please click on that link to approve or click on that link to deny that request. And as we know, mostly that our managers are pretty busy and that can take some time and you check the budget and okay. But you have some time gap there. The requester wants to know what happens within 72 hours. So we have two components in there, and we'll see that in a sample later. So we have then a manual intervention of a human, which then sends an event of approval or deny to that waiting orchestration, and then the orchestration decides to perform some actions, or if you have a timeout, do something else. But let's have a look at the code. The code is pretty simple too. It's just the orchestrator, not the action. Initially, you want to request some approval. You call an activity, which is just a function, which maybe sends out a mail or an SMS or something like this, and say, hey, can you please approve that action? And then you set up a cancellation token source, which is just your timeout, which we saw before. That's a durable timeout. We just create some timer, and then we wait here. And we wait here, we create a approval event, and then we create a second one, the timeout up there, and then we do task when any. And then when one of those completes, we check which one. And when the approval event completes, which just checks if somebody clicks the link and the database is an approve there, then we have, as a result, the approval event. Then we process the approval further, and we cancel the timeout. Or if the timeout wins, in the else there, we do some escalation and send again a mail, said, hey, we sent you a mail 72 hours before, you didn't respond, please now respond, somebody's waiting for you. And that's an option. So you have the option to bring in external events, you have the option to wait for something, and you can inject events. The runtime enables you to inject events. We cannot see that in the orchestrator here, but the event will be injected in the other function where we send an event. It's just one line of code to send an event in, and then the runtime checks, is somebody registered for that event? Yes. Then we bring up the orchestration saying, hey, we have an event for you here. Please process it. Last pattern is sub-orchestrating, which looks pretty similar to fan-out a bit, but of course it's not. Yes, it's the option for you to cut your workflows into reusable parts. And I think you can have that very often. It's not pro reusing code, it's just you have to know that on your own. You can have different workflows and don't execute them on your own. You have the chance to execute each sub-orchestration on its own. There's no limitation. So sub-orchestrations and orchestrations look the same. It's just how they are executed, if they are executed beneath another orchestration. That's what the runtime cares about, nothing else. How does that look like? I have a main orchestration up there which says, I want to sign all documents. And first of all, I pick a list of all documents we want to sign. And then I do something which looks like a fan out, but is not. I just call for each document, call a sub-orchestration which handles the signing of that specific document, which can differ from document to document maybe, and I don't want to waste that all in that huge orchestration thing, and say, okay, some granularity is good. We drill the functions down to a minimum, separations of concerns, and then go ahead and have here, and then we just started with call sub-orchestrator async. It's like calling an activity. And then that orchestration is beneath my orchestration. And of course, all of them need to complete. And finally, you just await them, like all other tasks. And how does the sub-orchestration look like? Like that one. I can call that directly. When I have a doc ID, I can call that single one and say, just sign that one. Huh? Or I have a big orchestration which has a list of, and then this orchestration calls my small orchestration to sign documents. And that, of course, that is just an orchestration. It doesn't sign. It just calls an activity which I create document copy, and then it calls a second activity which I sign PDF document and storage. Yeah? And that's the whole workflow we do here on 2 levels. And you can drill that to many, many, many levels. We'll see that in the sample later. We have some general patterns too. I call it patterns. Of course, it's not a pattern, but it's what to do in case of. We have errors. We have resilience retries, which is nearly errors, but not only. And we have the timeout. And I want to have a look on each of them, how you can deal with that scenarios. In case you have an error, what happens? Exception. We have a try-catch here in our function, and we call, in the orchestrator, we call the activity, F1, and that calculates an arbitrary value. And if there is an exception there in the code, the exception gets serialized, gets populated up in the runtime, and gets rethrown at that point in your orchestration. So it gets serialized because it has to go to the state handling. And then when your orchestration is raised up again and raising that point, there is no result for you, which you will get. They will throw an exception for you. And the exception is always of base type task failed exception. And then you have some information in there, just a wrapper, serialization wrapper. And then you can pull the information out there and check what you want to do. You can do some compensation. If you have a workflow and say, okay, we have the money from that account to that account. Okay, that fails. Compensation is money goes back to that account, okay? So, or, I don't know, clean the logs or something you want to trigger. You can, in that catch, you can normally trigger, again, activities. That's no problem. And you can have a try-catch in that catch. That's no problem at all. So you can have a decompensation inline there if you want to, maybe in a separate function. Yeah? You can scale it out. That works perfect even, that's a base principle, and that works perfect even in fan-in, fan-out. Yeah? So in fan-in, fan-out, in fan-in you would get a raise exception when you have a task when all. Then this is the point where the exception will raise, finally, there. And then you can decide what to do. Sorry. Second is retry. So we have seen the simple version of call activity, but there is a more sophisticated version. They built some resilient stuff in there already for you. So you don't have to pick a poly or other things because you can't use it with the runtime. You just want to check when I call a function which is deeply depending on resources which may be not available, like, I don't know, a flaky database, a database on a flaky connection, hybrid, or maybe an external web service, that's no problem. You just call activity with retry async and give the options in there. And I just wrote in 2 of the options. And on the next slide, I have a lot of more options there. You can define, for example, your first retry interval, after which time you want to retry. Do you want to retry? How many times? Maximum number of retries. You can, let's have a look. It's there. Maximum number of attempts you can define there. You can define your first retry interval. You can, the back-off coefficient, it's 1, so it's pretty linear. You can increase that, depending on the strategy. Max retry interval, everything you want to have there. Retry timeout, and custom. You can say, just in case, call me, and in that case, I will decide if we do a retry or not, depending on the error, or I don't know. So you're fully fledged there. You just pick the retry options there, and you're pretty safe. And then you can decide on runtime: do you want to retry, or how many, how often, and all the options there. That's pretty convenient. Yeah, and I think that's pretty important because you don't have a chance there to incept your resilience layer like poly or something like this at that point. Timeout. Timeout is. Yeah, what's timeout? Timeout is always asked for when you are waiting for something which probably runs pretty long and you don't want way too long. You can use that in various manners. The interesting part is the create timer here. Create timer on your context with a, let's call it deadline. Deadline is it's just a timestamp with a timeout here. It's just a date time. That's the deadline. It's the ultimate point in time. And you have you have a cancellation token here. Additionally, you want to use to have that timeout hanging on that token. You can even cancel that timeout with that token. So you have an activity task and a timeout task. And then you run both with the task when any. And of course, when the timeout wins, the winner, you can check the winner. When task when any gives you back the winner. If the winner is the activity, everything's fine. We just cancel the timeout, not that it raises up. Or if it's an else below there, because we have a return true, I don't need that else. If the winner is the timeout, you know, okay, I can decide what to do. Call it again, I don't know, do some backup strategy. What is the problem? And that's pretty easy. You just need a point in time, create a task with the create timer on the runtime, and the whole state machine there manages all the things for you. It just brings your orchestration, dehydrates your orchestration. You don't have to pay for, you're just waiting. And after the timeout, it comes up and says, yeah, is the other one finished? No. Okay, then the timeout raised. Okay, decide what to do. Pretty simple, directly in your code flow. I think that's the most important part. So, okay. I'm happy we have some time left. Real world sample. I create a sample in order to show some of the common patterns we have seen in theory there in some code. And I picked a pretty common sample which has been thousands of times implemented on AWS Lambda, but I think nobody has implemented on Azure Functions yet. It's MapReduce. It's a stateful MapReduce with that state engine, and I think that's pretty nice. How does that look like? I have the pattern there. The pattern is always the same. We have a lot amount of data, and we want to do some mapping. So we want to pick some data out, and then that's the mapping process. And then we want to reduce the data, which is some kind of grouping. I have a maximum value there. You can use averages, minimum, sums, whatever you want. Yeah, you just reduce the data. Yeah, that's map and reduce. And of course, you can use large solutions like, I don't know, Hadoop or something like that, Spark, whatever, and to pull your data through platforms that are made for that. But I think sometimes it's funny to build some samples like this and to see what this durable function runtimes can do for you. So initially, we have up there, we have an orchestration, which manages the whole process, map and reduce. And then we have two sub-orchestrations. I will show you code in a second. Which one orchestration is orchestrates the mapping, and the other one orchestrates the reduce. And then we have a fan out in each of the trees here, and we have a fan out here to do the work. Of course, that's the mapping work. And finally, we collect the results. And of course, and then when we're done, we go to the second one, and we have the reduce orchestration with, again, do some fan out, and then bring back the results, and then we have one, in that sample, we have one single number. I implemented some many times before implemented sample. I'm aggregating some weather data from the US from 2017. You can get that publicly available from them from an FTP server, large files with a lot amount of weather data in there. You have there's one temperature per line per station around in the US. So you have many stations in the US and you have many data, but just for the sample, I picked some of the files. And then the orchestra, just put that in a storage, and I will show you in the sample in a second how you can use that, even use that functions and that binding features to keep your functions more pure and more away from the implementation most time away from the implementation of what storage is behind and where does my data came from and where does it go to. Because that is the most interesting part from my perspective from Azure Functions is the binding. So your function can be roughly pure if you just use some base types, some common types. Yeah? If you string, datetime, integer, long, maybe some common base types like a stream. Yeah? Your function is independent from the implementation around. So just the binding injects the value into your function, and the function don't have to care about the technical implementation around. You still can switch your implementation at the end, at every time, and the function don't have to be touched. It's just the same function. It's just tested and it works. So, and I incorporated in the example the deeply binding features of Azure Functions to the storage there to abstract that at that point. So, okay, let's go over there. I will show you the code there in JetBrains Writer. I don't open Windows and Visual Studio there because it will suck up my battery. That's not good there. So I will bring it up in Writer. So you can. I developed the whole sample in Writer. So you don't have the option to say new template in Writer, but you just copy a default template and then go ahead. You can develop that wholly locally, even on a Mac. That's not a problem. The function runtime is running on Mac too. That's not a problem. Only the storage emulator, if you need some storage, the storage emulator is not available on Mac. So either you use that one in Azure or you have a Windows machine with a storage emulator there. But I use the one in Azure. I hope the network connection fits that here. Yeah, that's pretty simple. So let's have a look again at the. Let's go from there. MapReduce orchestration there. We have finally up front, we need a starter, which is not part of the process, but we need to start the orchestration, the first one. So we have that Async HTTP API sample there. Here we go. There it is. So I have an HTTP endpoint, yeah? And the interesting part is I use the precompiled version. There are the two versions of Azure Functions, the two runtimes and two versions of runtimes of Azure Functions. You can completely implement that without any attributes, and then afterwards you go and say, I have some binding information. I have that in my JSON files in the project, and then the runtime compiles it. Then it gets compiled and pushed to the runtime, and the runtime then evaluates the binding files. In that case, I don't use the binding files. I use some attributes, and the attributes finally got compiled. And from that compilation, there's a reflection there, and then he pulls out the information which the binding has to be. So for everybody who hasn't yet used the precompiled version, that's a trigger attribute, which tells the runtime, I want some HTTP binding trigger on that function. Yeah? I just declare it in my code. And I say I have the authorization level and I want to have get and post. And I have the orchestrator start client, and that's it. And then what I return here is exactly the status page I get created. And then my orchestration is running. So, and how does it look like? We start the orchestration here. That's the name of the orchestration, which is the name of the next function there, which is pretty slim. We have just a trigger there and the context, and here we go. So we have two actions there. Bring up front, I have a tuple there. We have my container names in there because there's my data in there. I need some data. We have files which are around 1.6 megabytes. There are a lot of files with a lot of data in there. It's just positional-based information in there. It's just plain text, which I downloaded from the FTP server from them and put it in my storage. And then I have a container where my input data is in there, and I have a container where my output goes to, my mapping output goes to. And it's just a tuple to tell the execution function where to get the data from and where to pull the data to. And I have a reduce container. Yes, that's the name of it. So, and the first thing is that orchestration causes sub-orchestration because it's not my job. I have an orchestrator for mapping, and he cares about mapping. So, and afterwards, when we're finished, we await that call. Then we will call the next one, the reduce orchestrator. And then, a surprise, we have a maximum and then we're done. Okay, let's go in detail. How does the sub-orchestration looks like? The sub-orchestration is pretty simple too. They're all pretty slim. First of all, we create a list of tasks because we will do some fan out there. And we just call another function, call activity, which get me a list of all files. This is pretty dynamic because if I have 10 files in there, that's my job list. If I have 1 million files in there, that's my job list, the files to process. The function is pretty simple. We'll look at down there, that's the get files from storage function. And that I just put in the container name. Because I have some attributes in there, say I have a storage account, that's the connection string is stored under that key. And then I create a binding here with blob. And I just put in my parameter, I put in here as a container name and say, I want to read on that container, please inject me a cloud blob container object there. So when my function is not aware of anything else, it just gets the container and just say, hey, list all blobs in that container. That's the job list. And function is pretty pure, and I totally used the ability here to inject that parameters as a parameter in my attributes. And runtime does the rest for me at that point. So when I have my file list here, I just do some loop, create the necessary information. What's the file? Where does it come from? And where should go the result to? That's just an anonymous type. Perfect serialized, no problem. And then I call my map data from file activity. And that's a fan out, because for each file, he just calls it and spreads the tasks out, and finally I have a list of tasks. And there's the await, there's the await for. And in that await, we await all the mapping. When all the mapping tasks are done, we're done with the mapping, and then my orchestration job is done, and then I just complete, and then the above orchestration will continue just with the reduce. How does that look like? And the map data from file is pretty simple. I just put in that data, I have as a parameter, that here, and then I use the data here directly in my bindings. I define an input stream and an output stream. So my function is pretty pure. My function don't know about containers, don't know about any other technologies. The only thing my mapping function gets is an input stream and an output stream. And that's the function. I have an input stream and a nested output stream. I read the header row, throw it away, and then read the end until I have reached the end of the stream, of the input stream, just reading. And every line gets mapped. I map the year and I map the temperature, and if there's no temperature, we just return null, because sometimes in the US there is no temperature. Ask Mr. Trump, I don't know. There's no temperature. And that's it. And we collect the results. That's you can even reduce that. The code could be more minimal, but yeah, for demonstration purposes. Map temperature. Yes, what's map temperature? If somebody asks, it's a substring. Map year is a substring. Okay, that's it. So we map the data out we want, 2 values, and write them directly in our output stream. Just year and then the temperature. It's a streaming operation. And that's totally streamed from the blob storage behind, because the runtime enables that. But the function don't have to care about the implementation of the stream. Could be a network stream, could be a file stream, could be a blob stream, could be, I don't know, S3 bucket stream, whatever you want, put a technology behind, bind it, and it works. Yeah, that's good. So, and when all the data is processed there, and our mapping orchestration is then done, yeah, we have a second container where there's a list of files. For every input file, we have an output file. And then we have the map data, which looks exactly like the original data, just that we have not 200 values in a line, we have 2 values in a line, which we extrapolated. Yeah? And after that, we are back again in our top orchestration, which then say, okay, if the mapping is done, we call another sub-orchestration, which is the reducer, which works perfectly in the same pattern, because, first of all, he pulls a list of jobs. That's the list the files we just created in the mapping. Yes, that's right. And it's exactly determined in the same way. I even call the same function here. Just put in the container and say, that's the container. I know that there's my input data in there. That's the output container of the last orchestration. And I just, again, loop, fan out. I call reduce data from file. Yeah. And then await all the tasks, fan in, have all the high values, and then a little bit cheating, I just take the maximum of all the high values and then say, okay, that's the final reducer. That's the problem of all MapReduce. And the implementation is exactly the same. It's nearly the same. For the reducer here, the reducer function, that will be a single function. And we just bind, again, the blob attribute, so we get an input stream, and the input stream just parses the values and just temperature greater than max temperature in loops, and then we just keep the max temperature. Of course, there are better functions for that, but just for demonstration purposes. Yeah, and then we return the highest temperature in that file, and that's it. So, and we just have a stream, don't even have to be a file. And that's pretty easy part. And even if one of the files clashes in the reduce, all the other results are still there. That's no problem. Of course, you have a external state because you have some files generated you're relying on in your storage, and if you delete the files, the orchestration cannot resume because you have some external state there. Yeah, you have to handle that on your own, but it's not the problem at all. So, and then you just pick the value, and then I see the time is running. I will show you that in a second, how that works in Azure. We'll start that right away. How the solution is running. So, I normally, many ways to deploy that, we don't care about. And yes, so that's our function app. I have a function app there and there. In the function app, I have a list of functions. We see get files from storage, map data file, and each of the functions in there, and it's pretty well hosted there. So it's ready to run them, and I have some complicated thing like Postman there. And I just will call the public endpoint. Yeah, it's not visible in the recording. Pretty good. I just call the public endpoint of my HTTP starter orchestration there, yeah, which I can get if I go there and I won't go there because then there's the URL above, and just paste the URL in there, and then I get. See, I've tested that a result. Let's do that again. Hope that's running. Come on. So I just restarted it, so we have the whole runtime ramp up again. That's the hard life of cleanup. I promise it's working in a second. So in the meantime, I will show you. I have a storage here, and yes, in that storage, that's one of the folders. There's the data in there. It's 1.7, 1.9, 1.6. That's all the weather files from 2017, not all, just some of them. We would wait for hours if we want to calculate all of them. There's the result. So my orchestrator, my starter orchestration starter, replied to me, hey, you have some URLs. Here's the URL for get the status. And then I click on the URL, and Postman opens a new tab, and I say, okay, let's see what's the status of the execution. And it say, hey, it's still running. I have no input and output for you, but it's still running. So we just poll, it's still running. Just working on the files. Still running. Normally took around about 10 seconds to complete from ramp up to thing. And then we will see, there we go, completed. It's completed, and the output is 41. 41 degrees is the maximum temperature of all temperatures in all the files I have in the storage there. So it's not that hot, but hot enough. Okay, so great. Okay, pretty easy to operate, and I think it shows pretty good how to bring all the things in practice there in a sample. So we have 2 minutes left for question and answers, and I hope it's 2 minutes.
No.
No. Okay. Okay. If you have no chance to ask me questions, I'm still here till night and maybe longer. I don't know. Just come to me and ask me. Do we have some time left?
Actually, yeah, it looks like the timer is stopping at the last minute.
Okay, let's.
Already 5 minutes overtime.
Okay, let's do it. Okay, we have a question there.
Very cool talk. Thanks a lot. A small disclaimer: I'm basically from AWS part of the world, so question could be a bit stupid, but here it is. So basically, there is like something that I want to have serverless, like classical, stateless, small functions, cost bananas. If they're dying, I don't care. In opposite side, I have like container, like managed Kubernetes, ECS, whatever. So basically, my question is, in your point of view, between those two patterns, where is the place for these durable functions? Why shouldn't I just throw it all to containers and forgive about it, but not writing C# code that could be kind of painful, for example, if you're a Python developer or not developer at all?
Oh, I've seen, yeah. I've seen many implementations. It's independent of the language. You can do many things there. I think the option to execute just a bit of code serverless and to have that scaled to a large number of infrastructure without hesitating about anything. Yeah? I've done solutions with customers where we process millions of files in a snapshot of time. Just we put the files in the storage and we have one function which processes, streams the files and analyzes the content and then puts the result in somewhere in a serverless table. And the function runs, I don't know, million of times in 10 minutes. And then I pay for exactly the 10 minutes. And that's it. And then I can even crash the whole infrastructure and say, okay, I delete the function. The work is done. I have massive capabilities in scaling on that serverless thing. Of course, this is an additional aspect. If you have serverless things, functions as a service, because you can have multiple other things in serverless too. If you function as a service, the best feature is that you just write a small function and want to host that function in an unlimited scale. And that's pretty one of the best arguments. But as it is in real life, you don't just have small functions that work on demand as many as you want. And often you have a workflow, maybe have your small workflow for some small functions. And that's the point where the durable extensions came in, because there is no orchestrator there. There is an orchestrator. If you are in Azure, you can use logic apps. You have logic apps, which is a serverless orchestrating engine. That's already is there. But if you don't want to use them, you just can put it in your code. I personally like the logic apps because you have many more features. You can monitor your orchestrations, but you have many more options there. You can call a lot of functions just from an orchestrator externally, but you need an external orchestrator. If you don't want to have one, maybe that's an option. It's still preview. I forgot to mention, it's not final. It's just in preview. Preview, I don't know. There's a release candidate next week or the week after. So be patient. There's still many work they're doing on that. It's still not complete. It's in preview. Okay.
Thanks, Sebastian.
Thank you. Thank you.